Okay, so this will be the explanation of example 13. It's a Tetris game that I made a little bit different. I created my own algorithm. You can do this in many ways. This is just one way to do it. Let's look at the scene first. So I have just four different types of pieces in this case. You can press S to make it move faster, and then you cannot. We have some colliders here on the edge. We cannot go past that. Um, Let me show you that it works. And then I'll explain how the pieces work. So now when I place this, we should remove one row here, you see. So uh, let's first discuss the elements that we use here. So we have these worlds here, the black ones, um, that have a collider that is physics based. And then on the bottom here, we have another collider, but that is not for a collision. It's just we raycast from the piece to this, and if we detect it, we place the piece. So that's what this is used for. So let's look at the pieces here. When the piece is first spawned, it has a collider that covers the whole piece. And then this piece also has a rigid body, so we move it with a physics system. When the way we place this piece is at the start of the scene. Here, let me show you. We spawn some holders. I call them holders. So the black area here in the middle is made by small holders. Let me actually say that one more time. So we have some squares with trigger colliders there. If I pass the scene here, you see we have these holders. I select all of them. Okay, so we have holders here. So we can take each square of the piece and snap them in place with using these. So what we do is we raycast from each square of the piece downwards to see if there is another piece below us or that edge collider. In that case, it's time to place the piece. So that's how it works. But like I said, when we spawn it, this has a collider that covers the whole piece that is physics based. When we place it, we unparent each square from this, and also these squares have their own collider, but this one is without physics. So we unparent each square, and then we delete the parent because we no longer need. So that's how this works. But because we raycast from each square below to other squares or the edge collider, when we spawn it, the physics layer of this of each square is the default. Once we place it, we change it to piece square here, because we don't want to raycast from the square to the same square. We're trying to avoid that. So that's how it works. Now, when we place a piece, two things happen. We spawn another piece, and also we check if any rows are full. And in that case, we delete those rows, but we also have to reposition uh, those the other rows when we delete one. So let me show you here. I have a drawing made in Paint, but I'd like to open it in Paint actually. So I'll show you the algorithm for this. I made a mistake. Let me just fill this with blue. Now it doesn't work. Okay, no problem. I'll make a couple square here. But before that, the holders, how do we spawn the holders? Let's look at the script first for the holders. So I just have a function. If you're familiar with two-dimensional arrays, that's how this works. Here we spawn the holders. So for each column, we spawn each row here. We have a prefab of those and we spawn this. And we also save. We save in an array some squares here. We save the first square in each row here, because when we destroy it, we destroy the rows that are full. We don't actually have these squares in. We don't save them anywhere, so we just get them at runtime by using these squares. So let's say we want row 0, we raycast to each square here, and we detect those squares and save them in a list. So that's why we save these, and we call those destroyer positions. So these squares, okay, the first ones are the destroyers position. So now to destroy those rows that are full, this is the algorithm. We make a list of integers. Oh, my bad. This is for because here we save the rows that are destroyed, because we'll need those later to reposition the other rows. So that's why we have this here. So we go from 0 to the last destroyer position, and then for each row, we count how many squares we have on that row here. So we have a list of squares. So we recast to each square, and if there is a square there, we just add it to the list. And then we say we check if that row is full. So if the square count is equal to the length of that area, which I called holder area X here. And in that case, we save that row, the number of that row in our list, and we destroy it here. So for each square in that list, we destroy those. So that's how we destroy it. But then we have to reposition the other rows, and that's where I run into some problems. So I'll show you how I thought how I made the first algorithm for this. So the idea is the following. We'll use that array. So not array, sorry, list of the rows that that we just destroyed, and we start from the bottom, So we start. So go here. This is not this. I mean, sorry, this one here, the orange one. So the blue ones are not destroyed. The orange, the one with the outline, the orange outline is a destroyed row. So uh, we start from here, and then we look one row above, okay, and then we take everything above that empty row like this, and we move it by one square below. But when we do that, you notice that this here, the other empty row here, also moves down one square. So we have to change the value in that array of that row by -1. We have to say -1 to the position of that. But this doesn't work in all cases. This does not work in. Obviously, like I said, we look at we start from the bottom. We find the first destroyed row. We take everything above that, move it one square down. And we repeat this process. Then we go to this one here and do the same. We look above, take everything, move it one square below. But this doesn't work if there are two destroyed rows next to each other. So this is another case where we have two rows next to each other. So we had to change the algorithm a little bit. Um, One sec. So we still start from the bottom, but when we find the first, actually, go here to this row. Instead of looking above to the next row, we now look above while there are destroyed rows there. So let's look at the algorithm here. Uh, so and actually every time we move stuff, we delete the destroyed rows that disappeared from the array. So that's why CR say while destroyed rows count is bigger than 0, because after we move stuff, we remove the destroyed rows for the list. So instead of looking one row above, now we look above while the row above is destroyed one. And we count how many destroyed rows are there. So we have a variable for that. I call it move amount because afterwards, when we move everything that's above, so in this case this here, when move it downwards, we move it um, 2 times because we have two empty rows in this case below. So this will represent how many times we move um, the pieces above. And this here represents the index of the row uh, above the destroyed rows. So by default, we say that is the one above the first one. So go here to this one and we say is this one. But then we say while this is a destroyed row, we go upwards one until we reach a row that is not destroyed. And then once we have that, here we move everything that's above that row, including that row. So we go from that row to 0. So basically, in this case, we go from this one to 0. And then we use the overlap point. This is kind of like a raycast, but it's just a point. So we want to, because we don't save these squares anywhere, we have to get them here at runtime. So for each row, we get each square and then reposition it one actually not one, the move amount. So in this case, two rows below. So you see here, he transform position, that's the position of the square. We say plus equal vector 3 down times the move amounts. So here we move everything, and then after that we want to destroy, we want to remove the destroyed rows from that list. And because we started from the bottom, we remove from 1 to the move amount of rows. So in this case, we remove this one first, which happens to be the one at the end. And because this is a list, the one with destroyed rows, when we remove this, now this one here becomes the last. So we remove the last in the list move amount of times, which basically represents the amount of destroyed rows. And then after that, the other destroyed rows that still exist in that list, we move them by 2 squares in this case. And then we have to also change the positions by that move amount here. Now let's look at the spawn piece function. So once a piece is placed, we spawn another one. So we use what we just said, we destroy the lines and reposition everything. And then we spawn a random one. So here you see we say a random index, we create a random index, we have an array of pieces. And then we spawn a random one for that array. We make sure that we place this script, the Tetris controller in the piece there. we save the rigid body to decompose, we move it here in this script, and then we give it the velocity here on the y-axis, so move it downwards. So this, how do we move it? Very simple, we get the horizontal axis. So again, this is -1 when you go to the left, -1 when you go to the right, and 0 when you don't press anything. And then this is for just for left and right movement. We do it in fixed update. Here we update the velocity uh, on the x-axis, so horizontally it moves speed times horizontal axis. And then for the vertical movement, when you press S, we double the move speed, and when we release that key, we return back to normal. Uh, now let's look at the piece here. Like I said, we raycast every frame from each square of the piece, and if there's something below it, then we place it. We check for the holder below each square and place it on that holder. So we do it in a coroutine while it is not placed. We have a bool here that lets us know if it is placed or not. Also, we have each square in a list here. We do it in the start function. We save each square in a list. So for each square here, so for each one, we raycast below it by 1 because the squares are also length 1. And then if we hit something, then it's time to place it. So first we stop the movement. So say velocity is now 0. Make it kinematic, the rigid body, so now it doesn't interact physically with anything. We say the current, because we also have the rigid body of this piece in the Tetris controller. So we say now that is null, so we can no longer move this piece. And then we place each square here. So we say for each square, we check if there is a collider below. And if there is a collider, we deparent that square. We place it at exactly the holder position, and we change the layer because uh, at the start when you spawn a piece, it is in the default layer, and when we place it, we change that to piece square because that's where we raycast. Because we don't want to raycast a square to itself. Uh, so once that's done, we say it's placed now. We spawn another piece and we destroy the parent because now these squares are not children of that anymore. So we can destroy that. That's it. That's how this works. Um, Let me see. I think I will explain the logic for repositioning one more time so that it's clear. Yes. So when we destroyed the full lines and reposition everything, so let's look at that again. It's a bit hard to explain, but I'll try one more time. So again, we have a list here which will have the indexes of the rows that are destroyed. So first of all, we go from each destroyer position. So like I said, it's basically the first square of each row. And then we look below each square and see if before each holder, sorry, before each holder, yeah, and see if there is a piece. And if there is a piece, we save it in a list. And then we look if that list, the count of that list is equal to the length of the area there. So in other words, if that row is full, in that case, we save the index of that row in a list and we destroy each square there. But now we have to reposition everything. So what we do is, again, we start from the first, I mean, not the first actually, the last destroyed row here. So in this case, this one. And then we check if there are others as well above it. And we try to find the first not destroyed row here. In this case, is this one here. And also we count how many destroyed rows are until that row. Uh, so once that's done, we take everything here above the destroyed lines, and we move it down. We move those down by how many destroyed rows are below. In this case, two. Okay, and then um, we remove those rows, those destroyed rows from our list. But now, let's say we have some destroyed rows in this part here that we moved. Those rows also were moved by two rows below. So then we have to change the indexes of those uh, by two in this case. So by the move amount. So that's how this example works. There are other ways to do this. Uh, Also, the movement can be done in other ways, because in this case we just move it with the rigid body with a certain speed, but you might want to move it with transform translate everything by one square. When you press D, for example, you move it by one square to the right. Also, you can make an algorithm where you save all these holders in an array, and all the pieces in a two-dimensional array. But this is just my version. So I guess uh, that's everything for the Tetris example.